can join us. Everyone who wants to join. Yeah.
What are the constraints? Yep.
Hello, Aurel. I see you here.
Where is Vereshchagin?
I'm here, sitting in my house.
No, you are just invisible. Yeah, here.
Okay. I think we can try to start.
Yes.
Yeah.
Okay.
Maybe slowly, but start.
Okay. So today we have a pleasure to have Cheuk Ting Lee, who will talk about information inequalities, undecidability, and tithings, I guess. So.
Yeah. Thank you very much for the invitation. So yeah, so today I'm going to talk about like the decidability of this conditional affine information inequalities and conditional independence implication with cardinality constraints. So yeah, so this work has been like partially presented at the information theory workshop, but this talk will be like a more like complete version. But then I mean maybe I still can't like cover everything in the paper. So yeah, so if you are interested in the details, then you can refer to the archive version of this paper. So in this talk, we will talk about we will establish the decidability of conditional affine information inequalities, which is like inequalities among entropy and mutual information on random variables, but we allow comparing against constant terms. So instead of just saying say xy is greater than or equal xx, you can say something like xxy is greater than or xx minus 1 or something like that. So yeah, and then we will also establish a decidability of deciding whether the intersection of the entropic region and a given affine subspace is empty. And we are also establishing a decidability of a conditional independence implication problem with a constraint that one of those random variable is binary. And then this is proved via reduction from the periodic tiling problem, which is has been shown to be undecidable. Yeah. So before we go into the decidability, then maybe we should first review the entropic region. So given a set of random variables x1 x1 up to xn, then the entropic vector, studied by Zhang and Yang, is the vector 2 to the power n minus 1 dimensional vector, where each entry is the entropy of a subset of those n random variables. So I mean, for say n equals to 2, then the entropic vector has its 3 dimensions. So the 3 entries, the entry will be what? I mean, the entry will be x1 and then entropy of x2, and then the joint entropy of x1 and x2. And in general, there will be 2 to the power n minus 1 such subsets. And then the entropic region is the set of such entropic vectors, like where like the distribution of n range from like any like discrete distribution. And if we take the closure of this thing, then we get the almost entropic region. And the almost entropic region is a convex cone, but the entropic region is not a convex cone in general. And this has lots of applications like network coding, secret sharing, and group theory, and then automated proofs, and so on and so forth. And then like on the problem of characterizing this entropic region, like using like the inequality that mutual information between x, y given z equal 0, then we get the following upper bound, which is the Shannon type inequalities. And then this thing is a polyhedron, so it is easy to characterize. But the problem is that like this is not sufficient, so there's still some gap between this outer bound and the actual like entropic region. And then there are like non-Shannon inequalities that is not implied by this outer bound. And then in particular, like Matus has shown that like the almost entropic region is not polyhedral. So there are like the number of facets is not like finite. And Chen and Grant have proved a nonlinear information inequality and conjecture that like this almost entropic region is semi-algebraic. And then Gomez et al. Has shown that like this entropic region for n greater than equal to 3 is not semi-algebraic.
Sorry, but can you just say maybe some few words? What is this nonlinear inequality? If it's just it's how many variables is there? Maybe it's easy to write or whatever.
Yeah, it's not easy to write this on the case n equals to 4, and it involves some square term, I remember.
I do not.
It is like and it is more or less based on the result by Matus. So they like I mean Matus has shown like a sequence of such linear information inequality, and this the inequality in Chen and Grant is basically, if I remember correctly, it's basically formulating this sequence of inequalities by like I mean you can find a non-linear inequality that is implied by this sequence of linear inequalities.
Excuse me, I do not remember exactly this inequality, but I have exactly the same memories that it was some quadratic form somehow approximating this infinite family of inequalities found by Matus.
Yes.
Mm-hmm. Okay.
Maybe Milan remembers it better.
No, I have question about this. So, is it known something? Is it known something? How far is this nonlinear inequality? Because we can have whether it touches the entropic region or whether is it some far approximation. Whether it is known something about this.
I don't know how close it is to the optimal, but like everything.
Okay, thank you. That's
I
just wanted to know.
I'm not sure about the numerical like results of how far it is from the inner bound and things.
Okay.
I'm not sure about that. So the problem that remains is that, I mean, not a problem that remains. I mean, there's a lot of problems like about this entropic region. But like one open problem is that like there exists like an algorithm that can verify like every true information inequality. That is like if I give you inequality on this entropy, like an inequality that we say that every like entropic region must satisfy, then can we verify that it's actually true? Is it true that all entropic vector must satisfy this linear inequality? So does there exist an algorithm that can help us answer this question?
For example, with rational coefficients, yeah? Or
Yeah, for rational coefficients, let's say. Yes, so this is not known yet. And then we will talk about like the closely related conditional independence implication problem, which is like you are given like a set of like conditional independence statements among like random variables, and then you want to ask whether another statement about like conditional independence is implied by this list of statements. So it's like whether like the mutual information, like I write like this for like the constraint that like the set of random variables in AJ is a conditional independence of the set of variables in BJ, conditional independence of the set of variables in CJ. And then whether this list will imply this thing. So yeah. So for example, you have like this example, which is like the contraction axiom in the semi-graphite axioms by Pearl and Pass. And then obviously this is a special case of the conditional information inequality, which is like we want to answer whether like a linear inequality among entropy is implied by a list of other linear inequalities. So because like this is a special case of like information linear inequality. Yeah, I mean, you can write it as less than or equal to 0, it doesn't matter. Then this thing is a special case of conditional information inequalities. And then about the semi-graphite axioms by Pearl and Pass, then is shown by student D, which is with us now. That like these semi-graphite axioms are incomplete. So there are true conditional independence implications that cannot be proved using these axioms. And then later he also showed that like this, you cannot like find a finite set of axioms that can prove everything. So the open problem is that like is the conditional independence implication decidable? So which means that do we have a program where you can input like this problem, and then it will say that whether this implication is true or not. And this has been studied like some special cases has been studied like Geiger and Pearl has. I think they have studied like the case where I mean most of these previous work are studying whether the semi-graphite axioms are complete in some special cases. Like when these constraints are saturated, like the union of ABC is the set of all random variables. And then there's this work by Neil Pertz, which show that like if we have a bound on the cardinality, which is a bound on the size of the support of all the random variables, then we can have a program to solve this. So this is decidable. But then in general, we still don't know whether it's decidable or not. So yeah, so in this talk, we'll show that the following things are undecidable. So first, like the intersection of the entropic region and a given affine subspace. So there's like the first deciding whether there exists a vector in this an entropic vector such that matrix A times V is equal to B, where A is a rational matrix, V is a rational vector. And also we all like as more or less a corollary, we show that like the conditional affine information inequality is undecidable. So it's like we want to decide whether V, like if V is an entropic vector, then whether A times V is like entry-wise less than or equal to B implies that C, the inner product between C and V is less than or equal to D. And also we proved that like the conditional independence implication with a binary constraint is also undecidable. That is like if we like in addition to the conditional independence implication problem, we also impose that x1 is a binary random variable. Then this will make the problem undecidable. So we have like an additional like cardinality constraint. We have a constraint that one of those random variable is binary. Then this problem cannot be solved by computers.
Yeah, very impressive. If just the first one, even not speaking about the next one, is very intriguing. So, and it's important that you have not the closure, but the set itself, the gamma n set.
Yes. So this is actually quite important. So if we do like the closure, then I don't know whether it's true or not. And I mean, the proof really depends really make use of like the boundary, like the strength boundary of this like entropic region, but not the closure of it.
Wow, very interesting.
Yeah, it is,
Okay.
it is quite strange. I mean, I don't know. I mean, I like, yeah, but later on we will see how it is used.
Yeah.
So let me see.
You-
So about
and
the-
there is a hope
yeah.
to prove this just in your talk, or it's something too complicated that we can only learn the statement?
I will go through like the main idea of the
Okay.
proof during the talk.
Okay.
Yeah, but maybe not all the details, but like the main idea is not too difficult. I mean, it is actually it's not too difficult to understand. It is kind of, yeah. So
Okay,
but
let's
maybe
see.
we'll see later. So yeah. So about the conditional independence implication problem, then maybe I will summarize like the stage of this problem, which is like, I mean, we can have three cases. One is like no cardinality found on any of this random variable at all. And when the other extreme is that we have cardinality found on every one of these random variable. And then in the middle, then maybe like we can, and in addition, we know that like the cardinality of some xi is less than or equal to ki, and we are given like this constraint for a subset of this random variable, but not all of them. So there are three cases. And then we can, and then like people has also studied the case where like we only talk about independence. I mean, probabilistic independence, but not conditional independence. So C is always empty set. Then in this case, then it is fine, it's axiomizable. So of course, like then it means that it's decidable. Then people has also studied the case for saturated like conditional independence. That means that this union is the sets of 1 to n. That like every of this random variable is involved in each of these statements. Then it is known that the semi-graphical axiom is complete here, so all the cases are decidable. But for general ABC, this is unknown. I mean, this case is the general case. This case is still unknown. I mean, it's still not. We don't know whether it's decidable or not. And then if we have cardinality found on everything that is decidable. So like the remaining like cases, no, I mean not the remaining case because it's solved like by this paper, that we have solved that for the case where we have cardinality found on subset of random variable that is undecidable. I mean, which is maybe a little bit curious because if it turns out that this is decidable, I mean, if it turns out that this is decidable, then it means that it means that like if you have no cardinality found, it is decidable. If you have all cardinality found, it's decidable, but you only have some cardinality found, it's undecidable. So it's like, I mean, something it's in between, but it happens to be harder than both of this problem. I mean, if it turns out that it's undecidable. So I mean, like if you ask me, I would kind of think that this this should be undecidable. I mean, so that the situation won't be too strange.
Yeah. And about the decidable case. So just can you say if we just have an elementary theory of reals with logarithms, it's undecidable or not?
So
or it's open, or what is the state of this? Sorry for
yeah. So I guess you mean the task is a problem on like whether you can whether the first order series of real with logarithm is
or exponent, of course. Yeah. So it's
So
somehow well known, but whether it's decidable or not.
I think that will imply that it will not imply that this is decidable. I think it will not.
No, not imply. But is it an open problem, or it's just I forgot everything about this. Maybe somebody knows this.
Like whether like the real number with
exponentiation. It's open problem or it's.
I think it's still open.
It's open
yeah.
problem, and
Yeah.
this is the famous Tarski's one of the famous Tarski's problems. This is completely open. Otherwise, everything would just simply just follow from this result.
Yes.
So no, sorry, but a lot of things would follow. But it is completely open.
But that something was proven, I think, using some non-standard analysis or something about this, or I have some wrong memory, maybe. Okay, forgot about this.
So I think like some people, I forgot the name. I have cited their paper, but I forgot the name. But like people has assumed that if that problem is decidable, then this thing is at most like, I mean, is at most like maybe pi 1. I mean, in the arithmetic hierarchy or something. I forgot. Like, but it means that there will be some upper bound on the hardness of this problem, but it doesn't imply whether this is decidable or not.
So may I have a question, because I don't understand. You have two cases: this no cardinality bounds and some bounds. So
Yes.
Do I understand it correctly that your proof of undecidability needs assumption of bounds? Yes.
Yes.
Okay, so
So-
it's some special, and so you cannot pass the proof to a general case of without bounds.
And it was just said on the previous slide that one of the variables should be binary, I think.
Yes,
If I remember
Aha,
correctly.
I see. So that's binarity, it's quite important.
Just
Okay,
one.
thank you.
And also
yes.
it's important the other can be arbitrary, so it's kind
Yes,
of
yes,
balanced.
you're right. You're right.
Combination. Okay.
You're right. So it's important that one of those random variables is binary, but the rest do not have any cardinality bound. So if everything has a cardinality bound, then it is decidable. But then, I mean, I mean, the proof basically rely on that, like one of those random variables has a cardinality bound. So we can like force some sort of structure on that.
Okay, now let's consider the proof.
Yeah, so yeah, well, maybe we will proceed to the proof. I mean, maybe before the proof, then maybe I will review what is the periodic tiling problem. So this is like the domino problem studied by Wang, is that like you are given like a set of square tiles where each edge has a color in it. Then you want to tile the plane with a set of with these tiles. I mean, you are allowed to use like each type of tile as many times as you want. But then like the tiles, the adjacent like edges, like the touching edges of these two tiles must match, like the color must match. So here is green and green, here is red and red, is blue and blue. And then, so the question is that whether you are given a set of this tile, then whether they can tile the plane. And then Berger has shown that like deciding whether a set of tiles and tile the plane is undecidable. And then the proof is by simulating a Turing machine using these tiles. And then because the whole thing problem is undecidable, so like this problem, the tiling problem is also undecidable. And furthermore, like Gurevich and Koryakov has shown that like the problem of deciding whether the sets of tiles can tile the plane periodically is also undecidable. So this is like what we will reduce like the problem from. So it is like we will convert a problem about intersection of entropic region and affine subspace to a problem about periodic tiling.
Yeah, actually, there is a result which the proof of Gurevich and Koryakov was they reduced the pair of inseparable enumerable sets. So if you are in one set, then the tile has no periodic tiling, and if you are in the other set, there are no tiling at all. So that you embed these two sets.
I see.
Mm-hmm. Okay, just comment.
Yes. Yeah. So I see like the remark on decidability of real exponential field. So it's like indeed. So it follows from like a conjecture, like the Scanio's conjecture on transcendental number theory, which I'm not very familiar about. But yeah. So and then like. Yeah, so maybe we will proceed to the proof.
Yeah, sure.
Let me see. Yeah, so the proof make use of this affine existential information predicates, which is just like a name of a function of like a statement of this form. So which is like we ask whether there exists a sequence of random variable u. I mean, u superscript L just means u1 up to ul. I mean, this sequence. So this is a statement which says that there exists. I mean, this is a predicate on this sequence of random variable x. So this predicate says that there exists a sequence of random variable u such that A times this entropic vector of x concatenated with u. So this vector is like the dimension 2 to the power n plus L minus 1. And then this thing, A times this vector is greater than or equal to P to be entry-wise.
And so, when you write u prime is, or what is ui or what is
it's L.
This is
L.
L. This is like,
oh yeah, just to say that the dimension is fixed.
L, I mean, it's
yeah. Sorry.
Yeah. So this thing, yeah. So this is just like a statement on the random variable x, which can be true or false. And then we will just make use of this kind of predicates to like we are just trying. We will just try.
Excuse me.
Yeah.
May I have a question? This UL, so it's a random vector or non-random vector?
Random, like
a vector of random variables.
Are vectors of random variables.
Without any bounds on cardinality.
So these are parameters for the affine inequality. Yes. These are like parameters of so the parameters are random variables.
No, the parameters are also random variables, but they are x. So we have x, and n variables, and we ask whether it's possible to add them some L variables so that some inequality is true.
Yes.
Okay.
Yeah. So one example.
So that's inequality for extended vector or possible extended vector. Okay, I see. Thank you.
Yes. So one particular example of this is that maybe like a predicate on x, which is predicates on x, which is defined as there exists u such that x of u is equal to 1/2 of h of x, which is always true, right? So this is like this an example of this kind of like statements. Yeah.
No, more interesting statement will be that, for example, the existence of a common information of some size or whatever. So it's a serious class, and we don't know how to solve problems for this class. But
indeed.
No, this one looks at this as something trivial because u is not related to x anyhow, but. Just the possibility, for example, to a network coding of some type or whatever, it's just all of this existential form. So it's very important class.
Yes, indeed. I mean, like for network coding problem, maybe you can formulate it using the like statements of this form. And also like a nice property of this kind of like, I would just say call it like AEIP. I mean, and then the nice thing about this AEIP is that like, if you take the conjunction between two AEIPs is still an AEIP, then I mean you can combine two AEIPs. And then if something is an AEIP, then you can also add more constraints to it, then it is still an AEIP. So it's like, I mean, you can pretty much combine it in many ways. And then it will still be AEIP. So this proof will basically work like this. So we will just construct a class of undecidable AEIPs. So like we will like incrementally like define like AEIPs like based on the things that we defined previously, and so that like at the end we will get an AEIP that is equivalent to the periodic tiling problem. And we will also be careful to only use like conditional independence, like which is like this mutual information equals conditional mutual information equals 0. And also like we'll use the cardinality bounds. Like I mean here you I mean it cannot formulate cardinality bounds, but later on we'll see how we can formulate cardinality bounds using inequalities. This one.
But if you use only conditional independence, does it mean that this B is actually zero vector or
yeah, so that is actually used in the cardinality bound. So we will need to compare against constants only in those cardinality bounds.
Mm-hmm.
Yeah.
Okay.
So yes, so so actually like this thing, I mean, it might look a little bit odd. I mean, because the constant term might look a little bit odd because like, I mean, usually people so like we study linear information inequality where there's no constant term. But actually, I mean, I would kind of argue that maybe like it's not too unnatural because like, I mean, we mix constants with entropy all the time. Like say Huffman coding. I mean, the length of Huffman coding is entropy of x plus 1. I mean, at most. And then like the expected length of the Kunoff-Yav scheme for random number generation is at most entropy plus 2. So yeah. So we'll have like addition. Like we add entropy with constant term all the time. And then there are actually some existing like examples of AEIPs that has been studied. I mean it's not all, like widely studied because like both of these are like my own work, but there are some examples of AEIP. So one is this like approximates infinite divisibility of information. I mean which says that for any random variable x and any L that is greater than or equal to 1, then we can find a sequence of IID random variables U1 up to UL, such that X is the function of U, of this sequence U. And then the entropy of each of these U is bounded by 1.6 over L times entropy of X plus 2.5. So you can basically kind of like approximately like partition X into L IID pieces. So it's like you can kind of divide X into L IID pieces, but then you will suffer from this penalty, which is 1.6, like a multiplicative penalty. So if this is one, then it means that I mean, if you and you don't have this constant term, it means that you are like basically breaking X into n pieces without any overlapping, right? But then I mean, but this won't be true. So in general, we would need like this kind of multiplicative penalty.
But let's just, maybe you can say what happens, for example, for the simplest case. If you have L is equal to 2, is it possible to split into two independent subsets?
It's in general not impossible if you want to do it exactly. If you just want like 1 over 2 here and then you don't want a constant term, then it is.
And if you have some just, I don't know, small constant like 1 plus epsilon h of x plus some small term or whatever, is it possible or not?
I don't know the optimal constant, but it won't be 1. I mean, you won't be able to approach 1. So I would like I guess it will be bounded away from 1. Like 1.6 is probably very close to optimal, I think, but I don't really have any. Yeah.
But even if you don't require identically distributed or it's important.
If you do not require identically distributed, I don't know.
Okay, Sasha, I think it should be different talk. It's a separate topic.
It's a different talk, but it's just So it's just like an example where you have a constant term here.
Okay, then maybe we can just go to the proof. It's not strictly necessary because if
we
look at all this, we will ask
question.
many questions.
Just question. So this result basically says that every random vector can be written as a function of some L random vector where the entropies has some bounds. Would be this interpretation of your result?
Yeah, you are right.
Okay, thank you.
Yeah, so the point is that like this is like an example of the AEIP because like you have a constant term here. And then this strong functional representation lemma is just another example which we will probably skip here. So, I mean, the point is that like entropy is not really like a homogeneous like quantity because like there are some sort of discreteness that's happening there. So it's like not unnatural to compare it against constants. So So maybe we'll go into the proof. So first, I mean, this is like probably like what the whole proof hinge on is the property that is shown by Zhang and Yang. They show that like if you have 3 random variables, and then like any one of them is the function of the other 2, and also they are pairwise independent, then each of these random variables are uniformly distributed over its supports. So this is like, yeah, maybe I will skip the proof, but this is like, yeah, but this they use this result to show that like the boundary of like the entropy region is like kind of like not so it is not a closed set. So that is something that's weird happening in the boundary. So it's like, I mean, if you impose this constraint, then the entropy of y1 can only be in the form of log of positive integer. So it's not continuous. So you cannot have something that's in between 2 logs. I mean, it must be a log of an integer. So yeah, and also this will imply that all of this y1, y2, y3 will have the same cardinality. And then now, I mean, because of this fact, we can construct an AEIP that checks whether a random variable is uniform, right? So I mean, a random variable is uniform if and only if there you can find another u1, u2 such that this together, x together with u1, u2 satisfy this thing. So now you can check uniform. And then if you can check uniform, then you can also check whether it's uniform with cardinality k. So the way you do it is simple. I mean, you just impose that it's uniform, and then you have some sort of bound on the entropy of it, so that it will force like the only solution of like log k between this number, like say alpha and beta. I mean, you just find alpha and beta to be rational number close enough to log k, so that if log k is between alpha and beta, then it implies that k is that number that you want. Because I mean, k is an integer, so you can obviously do this. So because of this, you can construct AEIP that's forced like that check whether a random variable is uniform, and then whether its cardinality is k. So basically, so this is the cardinality constraint that we will use like in this construction. And then now, I mean, we have a way to check uniformity. And then now we will check have a way to check whether x1 and x2 form a cycle. I mean, what the cycle means is that you consider the characteristic bipartite graph of x1 and x2, where you have like values of x1 on this side, value of x2 on this side, and then you have an edge if like the probability of x1, x2, I mean the probability mass function at this x1, x2 is positive. And then like this graph, you want to check that whether this graph consists of disjoint cycles, which means that like all of the nodes have degree 2. So this thing can be checked by this AEIP. So first you will need, of course, you will need x1, x2 to be uniform. I mean, this is what we need here. I mean, we would restrict attention to a uniform random variable here. So we'll check that x1 and x2 are uniform, and then the characteristic bipartite graph consists of cycles. So first they are uniform, and then there exists a binary uniform random variable u, such as x1 is independent of u, x2 is independent of u, and then x1 is a function of x2 and u, and then x2 is a function of x1 and u. And then u is also a function of x1 and x2. So if this happens, then the bipartite graph consists of disjoint cycles. So the way we can see is that, like, I mean, if we want to show that this implies this, I mean, if this disjoint cycle, then it implies this constraint is satisfied. So the u we will take is just maybe we will just take this, will be u equals to 1, then this is u equals to 2, and then this is u equals to 1, and this is u equals to 2. So basically you color each of this edge, so that's like any node, any two edges sharing the same node will not have the same color. So basically you color this is 1, this is 1, and this is 1, right? And then you will just take u to be the color of this edge. And then you can see that these constraints are satisfied. And then for the reverse direction, you basically they do the same thing. I mean, you basically take the U and then you construct the graph like using this U. I mean, because this uniform constraint, I mean, U is like binary uniform. It means that like the characteristic bipartite graph, basically it will have like a degree. Each node will have a degree 2.
Sorry. So this formula, you are just saying that the graph is of possible pairs consists of cycles, or also you claim something about the probabilities of these pairs?
Because they are uniform, so each pair will have a probability which is 1/2 times k, where k is like here k equals to 5. K is the cardinality of x1 and x2. Because like there are like 2k number of edges, and then I see what you mean, because there's
in your conditions you don't say this. Just formula express the property of the graph plus something about the probabilities or not.
I see what you mean now. Let me see. I mean, because maybe you can make this one larger and this one larger, this one smaller, and it will still technically satisfy these constraints.
No. Just what is your goal? Do you want to include this in?
Yeah. So we do not include it. So maybe the more precise statement will be check that x1, x2 are uniform with the same cardinality, and then also prepare x1, x2 is uniform over its supports. Over the support of this pair. So this will force that each edge has a probability 1/2k.
So this formula corresponds to the stronger claim.
Yes.
Yeah.
Sorry about that. Maybe I should have added this here.
Yeah. Okay.
Yeah. So, and then now, I mean, if like after we define this like cycles, then we can define like torus. So it's like a torus is basically a product of 2 cycles, right? And then, but now, I mean, because we can have cycles, we have a collection of cycles, these joint cycles. Then if we take the product, the Cartesian product, I mean, of these 2 cycles, then we get a collection of torus, like the torus. I mean, like I guess the plural is tori. I mean, it's like tori. It means that so it is like a statement about this x1, x2 and y1, y2. It will mean that x1, x2 will follow these cycles, and y1, y2 follow these cycles, and they are independent of each other. So you have, I mean, say x1, x2, the cycles look like this. Y1, y2, the cycles will look like this. I mean, maybe y1, y2 only consists of 1 cycle, and then the product will be these 2 torus, right? I mean, this torus and this torus, right? And now, I mean, now we kind of have something that looks like a grid. So the remaining question is like, how can we do tiling on this grid? I mean, yeah. So this is like what the remaining talk will be about. So we will basically use the torus as a grid to place the tiles. And then like one natural guess is that maybe we should just assign colors to each of these nodes in this chorus, right? I mean, a way to assign colors is that maybe we will just have one color random variable where its values correspond to the color, right? I mean, we will just introduce another random variable C, I mean, which should represent the color. And then like C is a function of x1, x2, y1, y2. It means that each node will only have one color. I mean, we can impose this. And then as long as we can like impose constraints that each tile, I mean each like say square, must have a set of color that belong to one of those permitted tiles. Then we are done, right? Then we can like form the periodic tiling problem using these tiles. But then this approach won't work because like we cannot just use the values of the random variables as colors, because like conditional independence or like entropy is invariance under relabeling. So it's like you cannot talk about values of random variables. So it doesn't matter that whether random variable to take value in 1 or 2 or red or blue or like something like that. I mean, the label does not matter. So you cannot really impose constraints on the values on random variables. So instead, we'll need some other way to make sense of this. I mean, to distinguish between different values of random variables. So the way we do it is that maybe we'll first introduce this statement. We will check whether f is Bernoulli 1/2, f is a pair of bits, and then g, conditional on f, is Bernoulli 1 minus f over 2, which means that like if f is 0, then g is either 1 0 or 1 with probability 1/2, or if f is 1, then it is always 0. And then v is like similar, but v is Bernoulli f over 2. So it's like it is only non-degenerate. It can be either 0 or 1 if f is 1. If f is 0, then v is always 0. Then this thing, then this is checked by these constraints, which I probably won't go into details because like it's just more or less just like I mean there's just a bunch of constraints that force this joint distribution to hold. Yeah, so we have this statement that check whether 3 random variables follow this joint distribution. And then we will define another thing called the switch. So the switch is defined as you have the sequence of W and a sequence of V and V bar. And maybe the W. Maybe we will just look at the case where k equals to 1. I mean, the case k equals to 1 will mean what? This statement says that. Maybe we will go into this step by step. So first, each of these W is uniform between 0 and 1. And then they are independent of F. So it's like F, we know that F is also uniform 0 or 1. So you can write it as this picture, right? You can write it as this square, where the horizontal coordinate is W